Welcome back. So I want to wrap up our discussion of chapter 14 on solutions by talking about a class of materials that fall somewhere not quite solutions, but not quite heterogeneous mixtures. They're sort of in the middle. And so I want to sort of look at mixtures in a little bit different way to sort of wrap up this chapter. So if we think about at one end of the spectrum, we have solutions, which are homogeneous mixtures. And then at the other end, we have what may one type anyway of heterogeneous, which we might call suspensions, right? So these are heterogeneous and they separate upon standing, like oil and water, right? You can mix it up, you put it back, it separates upon standing. Suspension. Now, these things called colloids or colloidal suspensions occupy sort of a middle ground in between something that is purely a homogeneous solution and something that is purely a heterogeneous mixture, or type what we might call a suspension. So they are technically heterogeneous, but they do not separate on standing. And so what allows us to generate these colloidal suspensions? Well, first of all, it's particle size. So particle size is in the area of 1 nanometer to 1,000 nanometers in diameter. So suspensions, if your particles get bigger, you're going to end up with suspensions, and your particles are smaller when you have a solution. The particles can coagulate, so they can come together, they can clump, but they don't separate. They can't pass through membranes. So they don't function like a solution in that way. And they exhibit some unique properties, which we're gonna discuss a couple of these, called the Tyndall effect and Brownian motion. So I've got a little error in my underlining here. So this is the Tyndall effect. So they exhibit the Tyndall effect and Brownian motion. So Brownian motion you're probably familiar with, and we'll talk about that. The Tyndall effect, probably less common. So let's first do a little survey of these colloidal suspensions, sometimes called colloidal dispersions. They come in various forms, and we're familiar with a bunch of them, right? We have what we call aerosols, right, which are really a liquid dispersed in a gas. So when we think about colloids, we have a solute and a solvent, right? So we have a solute dispersed in some medium, right? So we have this dispersing substance, which is like the solute, and we have the medium, which is like the solvent. So an aerosol is a liquid dispersed in a gas, like fog, right? Water droplets dispersed in air. Or hairspray, right? Little drops of that liquid hairspray, the material, dissolved in some sort of gas or dispersed in some sort of gas. You can have solid aerosols like smog or smoke. You can have things that we call foams, right, which have gas dispersed in a liquid, right? So it's the opposite. So this would be things like whipped cream or other types of foams, right? In this case, whipped cream would be air bubbles in a fat, right? In a liquid fat. You can have what we call emulsions, which are liquid and liquid. So you have a liquid dispersed in another liquid. So this would be fat in milk or fat in water. So when we take milk, right, we can form what we call homogenized milk, which doesn't separate, right? What we've really formed there is a colloidal suspension, right? Where we have that milk fat dispersed in the liquid water as a colloidal suspension. So it doesn't separate upon standing. So we have to homogenize it. And there's ways that you can create that homogenization. If you have non-homogenized milk, right? So you get it from the farm or get it from someplace, you notice that it separates upon standing. And you have other kinds like solid emulsions, right? Like opals, right? Or you have a liquid dispersed in some sort of solid medium. So in other words, there's all kinds of these colloidal suspensions. So let's look at the effects. Well, Brownian motion is that idea that was illustrated by the biologist Brown, right? And which was, we've watched a video in Chem 1, right, where this idea of Brownian motion is what eventually led Einstein to his mathematical provement of the existence of atoms, right? That there was motion going on. And basically, in our purposes, it just means that these particles are moving around in a random way, right? So they're moving, they're hitting other things, and they're moving. So they're moving in this sort of random, what we call Brownian motion. Now, the Tyndall effect is light scattering. So if we shine a light through a colloidal suspension, we can see the light passing through it. So in other words, that light is dispersed as it passes through. It interacts with the particles, and so we can actually see that light as it passes through. When you pass light through a solution, something that's actually a homogeneous solution, right, you can't see it pass through, right? So this here is a solution, right? Can't see it pass through. If there's this colloidal suspension, the light will be refracted, and you'll see the light. You'll see the beams of light as it passes through. Now, we commonly see this phenomenon when sunlight passes through windows, and you have particles in the air. So it's dusty air, for example, right? And you can see the beams of light, or you can see the sunbeams passing through those colloidal suspensions. That's the Tyndall effect. Now, one sort of classic colloidal suspension, right, is soap. So we've talked about soap several times, right? And remember, soap is this material, right? This special type of molecule that allows non-polar materials to become soluble in polar materials. Now, the reason it does this, or the way it does this, is because of the unique structure, right? It is what we call a fatty acid salt. Now, for our purposes, what that means is that it has one end of the molecule that is ionic, right? What we often call the polar head. And the other end is nonpolar, which we often call the tail of the molecule. So it has a polar end and a nonpolar end. The polar part is called hydrophilic, means water-loving, right? Water is polar, the polar head is going to be attracted to that water. The tail is hydrophobic, right? Afraid of water, right? Non-polar, won't dissolve in water, right? Think of it as fat, right? That's the fatty part. So what happens is these tails all try to hide from the water. And these soap molecules form these structures called micelles, which are basically spheres which have all of these polar heads pointing on the outside, creating the surface of the sphere, and all of these fatty tails pointing in toward the center of the sphere. And so the formation of these micelles creates an emulsion. Remember, that's a type of colloidal suspension. Right, where we have like what we have with like milk, right? Now, a micelle looks kind of like this, right? So we can see we have the hydrophilic or water-loving polar end on the outside being exposed to the water. We have all of these fatty tails pointing in the middle, hidden from the water. And so it's these micelles form when you put soap into water. So this would be an example of one of our fatty acids, right? Sodium stearate, right, is an example of a soap molecule. We have the nonpolar tail, the polar head. They self-assemble into these micelles in solution. And so when you put soap into water and you shake it up, right, you get a hazy solution. Right? That's the forming of our colloidal suspension, our emulsification, our emulsified solution. Right? Because we have all of these micelles which have the right size to form these colloidal suspensions. Now notice if we think about these micelles, right? They have a bunch of charged particles here, right? So these are all polar, right? They're ionic. They don't like each other, right? So these micelles do not want to get near one another, right? They repel each other. And so this keeps them from coagulating too much and forming just a big glob, right? So while they're attracted to the water, the different sides of the water, right, they don't really want to be attracted to each other. And so they're stabilized by these charge repulsions between the surfaces of these micelles. So that's just an example of soaps functioning as a colloid. Now, if we extend this to how soaps work, which we talked about a few chapters ago, right, in Chem 1, right? It's the like dissolves like, but how does soap allow oil to become solubilized in water? Well, think about it. What happens is the oil, right, what we're trying to dissolve, becomes trapped inside these micelles, or maybe not trapped is not the right word, right? It finds a home inside these micelles. So as when we mix oil with water, or in the presence of soap, instead of that oil just sort of floating aimlessly in the water and separating, it finds someplace where it's stable, right? Inside these micelles. And so what these micelles of soap do is they isolate the oil from the water. They keep that oil from globbing together. It gets trapped inside the micelles, which stabilizes it. And so you have the oil inside the being trapped inside the micelles, which are stabilized in the water because of the hydrophilic surface. And so this allows the oil to dissolve, quote, dissolve in the water, right? Or at least become stabilized in the water and be carried away down the drain, trapped inside these micelles. Yeah. So a little bit more detail about how soap works and the fact that soap, now we know a little bit more about it, it's a colloidal suspension, right? And that's why it's hazy, right? If you take soap water and you can get it to exhibit the Tyndall effect, right? You can see light pass through it. It looks hazy. All right, so that wraps up our chapter on solutions. So I invite you to contact me with any questions, and that goes anywhere along this. Be following along, not only with these videos to supplement, if you need to review things that we have in class, but also watching other supplemental materials that I might post as part of our daily assignments outlined in the weekly assignment sheet.